Same thing as last semester. I'm going to try and record all of the lectures, whether it's like Thursday. I'm obviously recording that one because we're not meeting at all, but I'll record these too. And that'll come in more handy this semester than it did last semester because we're going to do a lot of Excel stuff, and some of it's pretty bananas and like really detailed step A through Z, and you may get stuck on step M, and we're all still charging ahead, like leaving you behind. So you'll be able to come back to the recording, and that'll be helpful. But anybody know what this is a picture of? Hoover Dam, that's right. And actually, this is an old picture of Hoover Dam because they put in a bypass bridge. They were working on it when this photo was taken, but they figured that having all sorts of traffic going across the dam maybe wouldn't be as good as putting a bridge in. So it saves time and wear and tear on the dam. It does look 3D. All right, so here's the announcement slide. I put the lecture notes online, MU Online, in a variety of page formats, whatever you prefer, but I didn't put like announcement slides on there or blanks for it. So you'll just have to write whatever notes you'd like in the margin so you can keep track of what's due, or you can just look on the schedule, because if we don't have snow days, we'll just follow that. 2 years ago, last time I taught this class, we had 3 snow days during the semester. And for a 75-minute class, that can really make things interesting. But I don't think we're going to have any snow days this year. All right. So your first real assignment is due a week from today. And we're going to go over some examples in class today, some calculation examples that will allow you to start on the real homework assignment. I mean, the fun little handwritten cam scanner thing, you can get that out of the way in 15 or 20 minutes, but then start on the real homework, and then you won't have to worry about it on Monday night. All right, so any questions on the announcements before we get into it? Well, here's another interesting photo, just to get us thinking about hydraulic engineering and water resources. This is the Magdeburg Bridge in Germany. And it's a strange bridge because usually a bridge is so that cars can go over a body of water. But this is so that boats can go over a body of water. It's a canal going over a river in Germany. And the purpose of it was to connect 2 industrial canals. On the right side, the Elbe-Havel Canal goes towards Berlin, which is deep in the heart of Germany. And then the Mittelland Canal goes to the Rhine River. And the Rhine River has all sorts of cities along it, and it's kind of the industrial heartland of Germany. And so during the early 1990s, when Germany was becoming reunited, they realized that one way to rejoin the country, both symbolically and literally, was to make the inland waterways of Berlin connected to the rest of the country's water network. And so they built this water bridge at the cost of about $500 million. And it's the section that's dotted here in yellow that was built. And the other alternative to having this, it's a built-up dike where the water level is higher than the surrounding land. And so if there was a hole in this dike, then the water would start pouring into the neighborhood. German engineering, I'm sure it's going nowhere. But if they didn't have this, then what they would have to have instead was a lock and dam system where the boats would lower in elevation until they got to the river and then back up in elevation as they climbed out of it. And there is a lock and dam system on the Ohio River, over the course of many hundreds of miles. There are, I think, around 15 or so as you get down towards the Mississippi. But this avoided that, and it's just, I think, kind of a cool illustration of some of where we're headed. Later in the semester, we're going to be talking about open channel flow. At the beginning of the semester, we're going to be talking about closed conduit flow, or flow through pipes. And so towards our last lectures are going to be on the subject of channel design and looking at questions of when you go around a bend, for example. Believe it or not, the water actually tilts up higher on the side of the river that is on the outside edge of the of the curve. And so you have to take into account things like waves, even for a small channel like this, and the super elevation of the water as it goes around a turn. So that's where we're headed. More immediately, we're going to be talking about pipe flow. Hydraulic engineering is related to not only forces and pressures, but it's also related to the amount of water. And sometimes just as important as the amount is the when of it, the timing. And that's the case in a fire, for example. If there is a fire in a certain part of a city, it may be possible that the fire department, by extracting so much water from the pipe network to put out the fire, lowers the pressure so much that no one else in that part of the town can use their water. And that can have some negative consequences on water quality when you reduce the pressure so much that there's backflow. So timing is important, and the distribution of it. Pipe networks are very complex, and that makes it challenging to do the calculations related to the pressure at every location in a network. We'll start off by just looking at a single pipeline and doing calculations, how does pressure change in a line. But then when you add lots of junctions and water coming in and going out at multiple junctions, then the system becomes indeterminate, and it's you really need a lot of computational horsepower to get through problems like that. We'll be looking at water in several different places, like starting off in pipes, channels, reservoirs, and during the project you'll also be looking at water in the context of how much water do people actually consume. You'll be doing a demand estimation as though you were a design engineer looking at a new area that's going to be developed. And so we'll learn a little bit about the quantities of water that people use for showering, or for industrial processes, or for different types of commercial applications. And the interesting thing is that when you start talking about water, politics and economics immediately follow. There are few resources that are as important as water or that have caused as much conflict over the years as water. And we'll just get into a little bit of those social consequences and implications of water on the project. I know you're not a shy bunch, so please feel free to jump in with questions anytime you've got them. Yes?
Why are you not allowed to touch water?
I am. No? Yeah, I have a rain barrel at my house. And so you can put a barrel, the downspout that comes off your roof, and yeah, you're allowed to collect your own water. And in fact, the city of Huntington is really trying to encourage people to do that because as you may have noticed, anytime it rains, the streets flood here in Huntington. And that's because they sized the pipes before they decided to pave every square inch of the entire city limits. And so there's a lot more runoff now than there used to be, back when people had lawns and the horse-drawn carriages were going down muddy lanes. Water would infiltrate a lot more back then than it does now. And so the city of Huntington has several different initiatives trying to encourage people to use runoff water. And if you go over to the bookstore, Lotta's, you know where Lotta's is? Is that 4th? They've got a big rain garden in front where they've got some special plants that are supposed to be absorbing water and like evaporating it more quickly than usual. And they also have a big tank under a stairway on the side of the building that's taking water from the roof. So they're collecting it, and the city of Huntington stops by occasionally and takes the water out of their big storage tank to irrigate the flowers in town. Yes?
Do you have questions about that bridge on the Norris line?
Sure.
How did you mitigate any street flooding? I'm assuming there's some type of flood mitigation.
Yeah, I think that there are dams upstream and downstream of the Elbe. So just like the Ohio River is a managed river, and it's not really alive, the water levels are sort of, some guy at the Corps is pushing a button and the water level goes up and down in response. They manage it because they want to prevent flooding. It would really be an issue if the Elbe flooded and then you start scouring away that embankment. But I hope they thought of that. I don't know specifically. I've never seen it with my eyes, but I'm pretty sure that there are flood control dams upstream and downstream. Anybody know what this is a picture of? Well done. Pumps and pipes. You got it. Let's move on. Man, you guys are going to have a good semester. No, there's a name for pumps and pipes in a room like this. It's, oh, my clicker. What will I do? It's called a pipe gallery. This is at a water treatment plant. And so most probably someday you'll go on a tour of a water treatment plant or a wastewater treatment plant, and you'll walk down some long corridor that's just a maze of pipes. And that's one of the most challenging environments for calculating hydraulics, because they really prefer that the water pass through either a sewer plant or a water treatment plant under gravity flow. You know, they'll have some pumps because they got to lift the water out of the sand filters and put it onto the next step. But besides that, out of the sand filter, they're trying to have the water move from place to place just by gravity to save electricity. And so, you know, when we'll look at some energy grade line and hydraulic grade line diagrams through the semester, some of the most really intricate, detailed, and careful calculations are in water treatment plants like this. Now here's a picture of a watershed in the United Arab Emirates. And I've talked a little bit about my sabbatical leave last year. This is coming out of some pretty steep rocky mountains that have very minimal vegetative cover. And so when it rains, they have these flash floods that are so large that, you know, this channel is probably about, I'd say, 25 feet wide, trapezoidal channel that leads straight into the ocean. They're trying as much as possible to retain this storm water and have like groundwater recharge. They have several dams through the mountains, but there are still some places where groundwater recharge really isn't practical. And so even in places where you wouldn't expect it, where you'd think, you know, a desert like this, water resources aren't going to be as critical as someplace like here. But that's not true. Water is important wherever you go, whether it's a place where it rains a lot or maybe even more so in a place where it rains very little. The quantity, timing, and quality of water is a very important issue anytime that people are living someplace. I've got really nothing to say about this picture. It's in California, Northern California. I took this picture, so maybe it's just, you know, maybe I'm just being a little proudful about my photography here. Anyways, I do have something to say about this picture. This map is what you're going to be using when we get to the design project. And so it's a contour map where you can see there's elevations. These brown lines are elevations, and then there's some hypothetical city limits where a development is going in, and there are places outside of the city limits where there's going to be demand for water at various commercial and residential establishments. And so what a designer does is looks at some place that water needs to go from one place to another. And in this case, your water is going, when we get to the project, your water is going to be coming from a spring up on the top of a hill. And then you're going to do a series of calculations to tell me where the pipes should go, how big they should be, what's the pressure going to be at various important points in the city, how much the city is going to spend on the pipes, how big the water storage tank is going to need to be. And so you're going to learn a lot of really practical information as we go through the design project. And the purpose of it is to illustrate the principle of design. And the design process is, at the core, iteration. You know, doing things over and over again to try and optimize. Because, you know, if we wanted to, we could just put a 1 meter diameter pipe from the spring to point A, and a 1 meter diameter pipe from point A to point B, and that would probably be big enough. I mean, 1 meter is an enormous pipe, right? And more typically, a pipe going to a house maybe is going to be 5 centimeters in diameter. So you can always over-design and get the job done. But the art of engineering isn't overkill. The art of engineering is optimization and trying to find efficiencies and trying to deliver the system that just barely meets the requirements so that you can save your client money. And so you want your system to just barely give these people the amount of water pressure that is specified in the design requirements. And if you give them any more pressure, when you get to the end of this assignment, you're going to be really stingy with water pressure, because that's what costs money. If these guys want more water pressure, you have to make the pipe bigger, because that'll reduce how much energy loss there is through the pipe section. So you'll be going through here optimizing, trying to find little places to nickel and dime your network, trying to make it as small as possible to try and deliver the cheapest design to your client. And the design process of optimization is something that I think you'll really start to understand and appreciate by the end of the semester. This box? A hospital? This one? Yeah, that's the city limits. Yeah. So, I'm just so excited about the project. I almost want to just assign it to you today, but that wouldn't be productive. One thing at a time, one thing at a time. All right, let's talk about flow resistance. And flow resistance, I just realized if I don't look at my phone, I don't know what time it is. So I'm going to have to get a watch. Huh? 4:12. Really? Already? Man, where does the time go? I didn't have any text, by the way. All right, so flow resistance is a function of fluid viscosity. Remember when we talked about, when we were talking about Bernoulli's equation? Bernoulli's equation assumes that the flow is inviscid, because Bernoulli's equation doesn't know how to handle energy loss between points. And so Bernoulli's equation wanted to be for some perfect fluid that had no viscosity. Of course, there is no perfect fluid that has no viscosity. All fluids have viscosity. And so how much energy you lose and how much resistance a fluid encounters as it flows through a pipe depends on the viscosity of that fluid. And this picture is meant to represent the flow through a pipe, where you can see that there's a lot more turbulence at the edge of a pipe as water is flowing through it as compared to at the center of the pipe. A similar thing here, this is an open channel as water is flowing through a channel, and the cool colors represent lower velocities, the warmer colors represent higher velocities. So fluid viscosity is one function that determines how much energy loss there is, but the flow conditions also dictate how much energy loss there is. And the higher a velocity is through any kind of a conduit, the more energy is going to be lost as the water passes through that conduit. It can also depend on the cross-section geometry. And just to illustrate, consider this. So let's say you have one channel that is like really wide and another channel that is more rectangular in shape. So of these two channels, it's pretty clear that the top one, which is really, really wide, is going to encounter more resistance to flow, because more of the flow is close to this surface where friction is being encountered. And so, this area that's far away from any edge is going to flow without much interference from a frictional surface, whereas the furthest you can get away from a flow surface in a really wide channel like this is from the bottom to the top. And so that's what we mean by cross-section geometry, is sometimes the shape of the channel has an effect on how much resistance the flow encounters. Even if the cross-sectional area is the same, it can just be the shape of the channel that has an effect. Boundary roughness is talking about material type. And so whether a pipe is made out of a very smooth plastic or a more rough cast iron can have an effect on the pressure downstream. And that's another thing that in an optimization situation where you're designing a pipe network, the WaterGem software we're going to be using this semester, you can change material properties and see how much energy loss is occurring as you switch from one material to another. Okay, so we all remember the cutoffs and thresholds for laminar versus turbulent flow. In the case of laminar flow, there's still energy loss. It's just that the laminar layers, you can think of water as going through a pipe, and there's a series of layers of water. And this layer of water is going faster than this layer of water, and the speed is decreasing. And so this layer is slipping over the layer above it and so on. And so the energy loss is less than there would be in the case of turbulent flow, because in the case of turbulent flow, most of the energy loss occurs as the water is interacting with the roughness elements on the pipe. And we'll talk a lot about the boundary layer, which is the thin cushion of water right at the boundary of the pipe wall, and how the roughness elements projecting into the water can affect how much energy is lost. All right, I've showed you the Moody diagram before. Let's do a quick example just to illustrate how we can determine the friction factor F. Now the friction factor F gives you an idea of how much energy is going to be lost in a system, and it's used in the Darcy-Weisbach equation. When we're trying to calculate how much energy loss there is due to pipe friction, the formula is FLV squared divided by D2G. And so F represents the roughness of the pipe in these circumstances, because F changes if you've got lots of flow versus a little bit of flow. And F changes even for the same material. Even if you've got concrete, you'd have a different F value for a small diameter pipe compared to a large diameter pipe. So it is both material specific and circumstance specific. The first thing that you do in a calculation like this, let's say that we have a velocity given, 30 meters per minute, and so that's the velocity of flow. The diameter of the pipe is 0.25 meters, and the K sub s, sometimes that's also called epsilon, that's the equivalent sand roughness, is 0.26 millimeters. So what you do is you calculate the relative roughness, so the ratio of the K sub s to D, and you find out which of these curves you're going to follow. The next step is to calculate the Reynolds number. And from fluid mechanics, we had the formula that Reynolds number can be calculated as the velocity times the diameter divided by the kinematic viscosity of the fluid. And a typical kinematic viscosity for water is 1 times 10 to the minus 6th meters squared per second. So in this example, I'd like you to calculate what F value should be used in this case, where we've got water flowing through a pipe. We don't know what kind of pipe it is, but we do know the K sub s value of that material. We know the diameter of it. You're going to need to calculate the Reynolds number, and once you find out where they meet, where the curve and the vertical column of Reynolds number meets, then you follow it left on the vertical axis on the left side. I don't know why it would think that I should use Microsoft Edge as the default application for PDF files. But luckily, they've got Acrobat. All right. So we find the velocity in meters per second because we're going to need that to calculate the Reynolds number, right? And knowing the fluid properties of water, fluid properties of water, the diameter of the pipe. So we got the Reynolds number. Now the K sub s to D, we got to calculate that ratio, and it's pretty close to 0.001. So what that means is, over here on this curve, here's the 0.001 curve. We're going to be slightly above that because it was 0.00104. So we need to be just a tiny amount higher. So we're going to follow this curve until we intercept the Reynolds number that we've got. And back from that calculation, it was 1.25 times 10 to the 5th was the Reynolds number. So it's a logarithmic scale. Here's 1 times 10 to the 10 to the 5th. Here's 2 times 10 to the 5th. This one right here is 1.5. So we're going to be between 1 and 1.5. So here's 1.25. I'm going up until I intercept this curve right here. It miraculously happens to be a value where we can go over to the left really easily and find that the F value is 0.022. So this is a graphical method of finding the F value. There's also something called an implicit equation that's really accurate at calculating F values. That's the Colebrook equation. And I'll show you the Colebrook equation in a future lecture. That's how so you don't have to mess around with this figure. And then there's also an explicit equation called the Jane equation, which estimates an F value. And it's not valid over the same wide range that the Colebrook equation is. But the Jane equation is pretty good, and the advantage of that is that you don't have to iterate to find where the F value converges. You just can calculate it directly. Any questions about the basic idea behind this example or the specific calculations themselves? So what we basically did is just found the intercept of the curve and the Reynolds number line and followed it to the left axis for 0.022. All right. Now, consider a pipe that is inclined, and what we want to do is we want to think about the forces that are acting in the direction of the pipe. So since it's inclined, the direction axis that I'm interested in isn't just the horizontal axis, it's the inclined axis that the pipe is flowing along. So we can know that at location 1 there's some pressure in the pipe, and there's an area related to the diameter of the pipe. And we know from before that force is pressure times area. So there's some force of the water outside of the pipe pushing on the water that's inside the pipe. Like if we were going to draw some control surfaces and say that, you know, here's our control volume, the water inside this pipe section. So there's a force acting on the outside pushing this direction in the positive axis from 1 towards 2. There's also water on the outside of the pipe at location 2, and it's going the opposite direction because pressure acts in all directions, and so if we cut the pipe with the control surface, then the water that's on the outside of that control surface is going to be pushing back, even though the flow maybe is from 1 towards 2. Even though the flow is going towards the right, the pressure can still be to the left on the outside of that axis. And so what we can also say is that there is a shear force that's pushing to the left. It's the resistance, or the pipe friction is in the opposite direction of flow. So here, the water is flowing from 1 towards 2, so that means to the right. So you'll notice here, this arrow, that's representing the pipe friction force that's being applied. Now, what about the specific things here? First of all, L is the length of this pipe segment. That's what L means. P is the perimeter. So that's the area, the length, or the distance around the outside edge of the pipe. So P times L is the surface area of that pipe section that we're looking at. So that's PL, it's the area. And the shear stress, here this shear stress multiplied by the area of the pipe will give us a shear force. And so when we're talking in terms of force, you know, the external force due to pressure and area on both sides, well, since the water is flowing, this shear force is the effective friction that's slowing down the flow, and it's actually what causes a reduction in pressure between 2 points. The other force I want to point out is the weight of the water. And so here in this pipe section, there's a certain amount of water, and water has a unit weight of gamma, and A times L, what is that? A times L. It's the volume, right? So the volume times the unit weight gives us the weight of the water. And here, since it's inclined, they're saying that the weight of the water is down, but we could also find what component of that weight of the water is normal to the direction of flow. So the whole point of considering these forces so carefully in this pipe section is that we could set it up as a force balance. We could say that it's in equilibrium. P1A1 is to the right, P2A2 is to the left, and that's why the negative sign is there. And then we have some component of the weight of the water that's going in the positive direction. That's this arrow. And then the shear force is resisting flow. And so all of that is in equilibrium. When the water is flowing, the forces are in equilibrium because it's not accelerating. It's moving at a steady velocity. What do we call that when conditions are not changing with respect to time? Steady flow or steady state, right. So conditions are steady with respect to time when things are in equilibrium. That's the case here. Well, we can change some definitions around. We can say the change in pressure with respect to the unit weight, we're going to call that H sub F. And if you look here at the definitions, H sub F is related to this S sub F. H sub F is the energy loss, and you're measuring it on the energy grade line. Hydraulic radius is what R stands for. And hydraulic radius is the area of the pipe divided by its wetted perimeter. And the wetted perimeter, in the case of a circular pipe, is just the perimeter of the pipe. And so for a circular pipe that's flowing full, since area is pi d squared divided by 4, and the perimeter of a pipe is pi d, then the hydraulic radius, which is A divided by P, that's just going to be d divided by 4. That's just for a circular pipe. There are going to be other times where you'll have to calculate the hydraulic radius, and it won't be quite that easy. But for a pipe flowing full, we do have that simplification. So with these two simplifications in mind, we can rearrange this equilibrium equation and say that the amount of energy loss is related to the shear stress, the pipe length, the unit weight of the fluid, and also the hydraulic radius of the pipe. And then for a circular pipe flowing full, that little simplification where we substitute in d divided by 4 for hydraulic radius. Now we've got this for the H sub F. So we can use that along with the definition of the slope of the energy grade line. S sub F is how much energy loss there is divided by the length of the pipe. And this formula to calculate the shear stress is something that you're going to need to use on the homework assignment that's coming up due a week from today. And so make note of this. What it relates is how much shear stress is being applied by the fluid to the pipe, or you can think of it the other way around. You can think that the pipe is also applying an equal but opposite amount of shear stress to the water as the water is flowing, and it's a function of the hydraulic radius and the slope of the energy grade line. Now, speaking of slopes, there's two different S's that are shown here. When we have open channel flow, there's even a third type of slope that we're going to talk about. There's the pipe slope, but that's different from the slope of the energy grade line. And when we were drawing energy grade lines at the end of last semester, you may remember those sketches that we did, right? Where maybe we would have a tank of water, and there's some pipe coming out of the tank of water. Remember how we did these drawings, and here's the water coming out of an opening, and so we'd have our EGL start at the water surface, and it would end a little bit above it, and then it would continue. So this was our EGL. Here, you can see that the EGL has a certain slope. You can say, you know, how much energy loss was there over the course of some pipe length, L. So the slope of the energy grade line is how much energy loss there is over some pipe length. That's the definition of the slope of the EGL. The slope of the EGL is different from the slope of the pipe. In this sketch that I've just put on the whiteboard here, that's a horizontal pipe, or nearly so. The point is that the two slopes are independent of each other. You don't have to have the slope of the energy grade line equal to the pipe slope. You can calculate it in a number of different ways. It depends on what information you start with. Often you'll have the pressure at one location and the pressure at another, and so you'll be able to calculate. The only difference in the energy equation will be the losses, and so you can calculate the HF from that. In fact, our next example will address that same question.
Is the energy grade line always going to be steeper than the pipe line?
That's a great question. Sometimes it's parallel to the pipe. Sometimes its slope is less than the pipe. It's completely independent of the pipe slope. Now, when we do later in the semester start talking about open channel flow, there's going to be three slopes, because there will be the slope of the channel, there will be the slope of the energy grade line, and then there will be the water slope. And in uniform steady flow, those three slopes will be equal and parallel. But then in situations where the water is getting deeper or shallower, then those slopes are all completely different. And some of the most interesting stuff we do with Excel is trying to predict what the water depth is going to be some distance upstream or downstream from where we're interested in. But that's just all in due time. For now, we're talking about open channel, closed conduit flow. And so let's take this shear stress example. I really need to figure out some sort of a better clock. We've got 8 minutes to do this till we run out of time, and I think that'll just be enough. All right, we've got a 150 millimeter diameter pipe, and its physical slope is 0.1 meters of vertical per meter of length. That's the interpretation of m/m. It's the vertical distance per horizontal distance. The observed shear stress is 45 newtons per meter squared. We want to find the slope of the energy grade line, and then based on that energy loss due to pipe friction, what would be the pressure change over 100 meters of pipe length. So if you look at this pipe, it's going uphill. So from one point to the other, part of the pressure change is going to be because of an elevation difference. But we also want to take into account not just the elevation difference, but we want to find out what would the pressure be at some downstream point because of the energy loss that the water is experiencing as it interacts with this pipe material, as it flows downstream. So you can see here's a sketch of the energy grade line, the hydraulic grade line. So I've given you two equations here. You're going to need to, with the known shear stress, rearrange this equation to solve for S sub f. S sub f is the slope of the energy grade line. So find S sub f, and then we're going to use the energy equation. And if it was a particularly long spring or Christmas break, you may have forgotten the energy equation. So that is V1 squared divided by 2g plus Z1 plus P1 divided by gamma is equal to V2 squared divided by 2g plus Z2 plus P2 divided by gamma plus H sub f. That's really like a quick and dirty version of it, where we're ignoring the kinetic energy correction factor. We don't have a pump. We don't have a turbine. It's just energy losses. All right, so in part A, calculate S sub f. And then in part B, we're going to try and find out what is the delta P when you substitute in a calculated quantity for H sub f. So substitute into there, and also you're going to have to substitute in some elevation for location 2, assuming that location 1 has 0 elevation. All right. So let me pause the recording and stop talking so you can start crunching some numbers. Let me show you this solution here. I'm keeping you late on the first day of class. That is, really? Well, I'll pay it back with dividends. All right, so let's just take a look at this. So we've got the hydraulic radius, 0.0375, and you can solve for the slope of the energy grade line. So 0.12232 meters per meter. That's a downward slope. You're losing energy in the direction of flow. So one thing I wanted to mention is the slope of the energy grade line and the pipe slope are independent of each other. We already talked about that. Now, to calculate the pressure change in 100 meters of pipe, remember both the elevation is changing, but you're also having a pressure change due to the pipe friction. So here's the energy equation, and what I did is I said since the pipe diameter is the same, the velocity at any 2 points is going to be equal. That allows me to set V1 and V2 equal to each other, and I can just cancel that out of the formula entirely. The next thing is I'll let my vertical datum at location 1 be equal to 0. And so what I am doing then is, since the physical slope of the pipe is 0.1, that means over 100 meters, the elevation at location 2 is going to be 10 meters above where it was at the starting point. So that lets Z2 be 10 meters. Now I need to calculate how much energy loss was there, and there's 12.232 meters of energy loss. And so the pressure is going to be different both because the increase in elevation, that means the pressure is going down, and the pipe friction means that pressure is going down. So location 2 is going to have 218 kilopascals less pressure than location 1 did, assuming that they're 100 meters apart. All right, so it's 4:47. I owe you some time. Let me just hit these announcements one last time and remind you, do not come to class on Thursday. Instead, watch the link, the video that I'll send you the link for. We're going to have an online class Thursday. All right, see you next week. Don't forget about the assignments. Yes?